Thank you, Joe. All right, so our next speaker is from ExxonMobil. Please welcome James Hannon. He's the Product Technical Advisor for ExxonMobil.
Good morning. So my name is James Hannon, but you can call me Jim. And I'm Product Technical Advisor for ExxonMobil with a focus on our turbine oils. So today we're going to do a little deeper dive into the technical aspects of gas turbines. And so we'll show you some pictures of gas turbine internals and that kind of thing. So a little bit beyond the scope of natural gas conversions that we've talked about earlier today, but building on this nation's move to natural gas, and then in particular the number of natural gas turbines that are coming online, and then gas turbines that are currently in the market today. So my talk today kind of gives you a behind-the-scenes look as to how ExxonMobil goes about developing a gas turbine for the market. And most people not familiar with turbine oil business would prefer that we had one turbine fits all. So why do we have to have so many different types of turbine oils? And that same question gets asked by our marketing people that would love it if we had one turbine oil, and also from our manufacturing and from our salespeople. It would make the world a lot simpler for us if it was just one oil fitting all applications. But what we find is many turbines have unique issues surrounding them that we find that we have to design to work with that particular turbine OEM, or maybe that turbine OEM has a specific requirement, approval requirement that's unusual to the rest of the industry. So unfortunately, we find ourselves in a position where I've probably got 6 gas turbine oils in the market. And that can get kind of complex to somebody that says, hey, look, I just want an oil that meets spec and not have to worry about it too much. So what we'll do is we'll show you the work we've done to develop a turbine oil specific for gas turbine applications and specific for gas turbine applications that have a common reservoir with the hydraulic system. And that element right there has been problematic for the industry. And those of you that are working at gas turbine plant sites, you're familiar with the term varnish in gas turbine, and then the impact that gas turbine varnish can have, whether it's a Monday morning no start, you go to start the plant up and it doesn't come online, or if the turbine is running and if there's a load modulation and then that turbine trips offline. So those are 2 significant events that we have been working hard for the past probably 20 years to improve upon. Once upon a time, we were putting our old steam turbine oil into these gas turbines and expecting good performance. And by and large, a number of these turbines would have these issues where we would get called maybe 18 months of service on a turbine oil and come to find out that we were developing varnishes and sludges within that turbine hydraulic system that would cause a turbine to trip offline. So that sent us, our R&D group, to the drawing board as to what can we do to improve the characteristics of this turbine oil. So we'll walk a little bit of background, a little bit about when we develop a new oil. Certainly we go by the OEM spec. That's kind of your starting. You got to meet the OEM spec. Then there's industrial international specifications by ASTM, by ISO, and you have to meet those also. But we like to take it a step further, and we do our own in-house rig development testing. So we, in our Paulsboro location in New Jersey, develop these rigs where we test oils and we can get a comparative relationship of how one oil does versus the other in an accelerated format, and then that gives us the confidence to take a product to market. We'll talk about an oil that we have in the market today and why we're so confident that this oil does has kind of cracked the code of varnish. Then we'll also talk a bit about system preparation, because many times you can develop the greatest oil in the world, and yet if the system that you're filling it into has still residual varnish and deposits from the prior charge, you're setting yourself up for failure. So we'll just kind of step on a few of those elements. So by way of background, ExxonMobil and other major oil companies have been in the turbine oil business for years and years and years, and especially back when the majority of power production was steam turbines from coal, our primary focus was in steam turbine oil. As the gas turbine population has grown over the years, there's been much more emphasis on producing a gas turbine oil. And part of that is we brought oils to market, and only to find that customers weren't satisfied with the performance. And so what we did was we did a survey, and it was kind of an interesting time for us, where we had our marketers call customers like yourselves and talk to plant managers, talk to maintenance managers, talk to anybody at a particular site that would have some knowledge of that facility, and then particular issues that facility was facing. So when we did that survey, we represented 192 gas turbine plants, 626 gas turbines. These were all EAs and FAs. So we looked at kind of the lion's share of power generation market, and from that, we learned a lot of great information. I just share with you two key elements here, that 40% of the customer base said, yeah, we have had a varnish-related issue, and that issue is either a trip or a no start, and our time frame was from overhaul to overhaul, because that's our expectation, is when you put an oil in a turbine, you want to get it from overhaul to overhaul, and that allows for optimum maintenance on the customer's standpoint, so that he can do his oil change during an overhaul, as opposed to having a scheduled downtime in midstream. That really becomes important. We at ExxonMobil have quite a few of these gas turbines in our refineries, and those refineries, they're running 8,400 hours a year. They don't have any downtime, and their overhaul time periods are very tight. So when we're talking about running overhaul to overhaul, our own company wants us to push that. The typical GE Frame 7 EA and FA overhaul time frame is 48,000 hours, and many of you are probably working within those confines. But our refineries are always pushing the envelope here, and looking to extend that out. And by and large, we're probably pushing into the 60,000 hours, and then pushing from a 6-year to an 8-year. And so they're looking for ways, and if your oil is the weak link in that conversation, that's not a good place to be. So again, that was more impetus for us to go back to the drawing board and see what we could do to improve on the technologies that we currently had in place. The other thing that we learned here was it transcends lubricant brands. So that's a fancy way of saying everybody was guilty. Nobody got a free pass. All the major oil suppliers were identified as, yeah, we've had varnish with that turbine and that type of thing. Now, what we're not showing here, there's a lot of story behind the story on how did we get there, and maybe it was the initial fill and flush. Oftentimes, now, and Al talked about this at the end, the OEM or ASTM or different external guidance will tell you to use a sacrificial oil on your initial turbine flush. So you'd run that sacrificial oil, drain it off, and then do your final fill. And what that does is removes any chemistries in there that might act as a pro-oxidant out of that system. I would say probably 80% of the time the EPC, the contractor, skips that step. And because they're looking at two things. They're looking at cost and time. And when I'm showing up there saying, hey, you got to do a flush, they're like, you know, talk to somebody else, because as a contractor, they're warranting that run for a year. And guess what? You can pretty much get a year's worth out of doing a poor flush job. So oftentimes, it's the customer after the fact, year 2, 3, 4, that has the problem that they don't know about because they just showed up on site after the turbine was built. So part of our survey, too, was asking, do you know if a sacrificial flush was done? And by and large, probably 70% of the people say, I have no idea because it got turned over to us and we don't know what the status of that prior load was. So there's a lot of kind of story behind the story in this survey, but our big takeaways were, regardless whether they did a flush or not, there's a varnish issue and it's impacting 40% of the fleet. At 40% of the fleet, that's a pretty sizable number. So that told us, hey, we got to do something about this. So when we look at trends and different things going on in the industry, a couple things to point out. One is customers are saying, hey, I need trouble-free operation from overhaul to overhaul. I can't afford a no start on a Monday morning. I can't afford a utility trip. And the demand penalties, and you know it better than I, that when you can't start that turbine up and you're a 6-hour delay, that's a major impact on your economics for the day. So that's certainly a number one element for us. The other thing is, as the dry low NOx burners came online over the past 20 years, what we found is the air-fuel ratio precision had to be a lot tighter than it had been in the past. In the past, you could get away with a little bit of sloppiness on that air-fuel ratio stoichiometry. But now with dry low NOx burners, you have to be right on. And so being right on means that my hydraulic servo valves that control air and fuel have to be right on. So if I've got the least amount of sludge or varnish in either the upstream pencil filter or in the servo valve itself, it's going to be a bad thing relative to hitting that air-fuel ratio. And if I'm off by a little bit, that unit will trip offline, and then we have, you know, those issues. We've also seen an increase in cyclical firing, and then yet, you know, this was written a couple years ago, and a couple years ago, a lot of the plants that had started base-loaded are now cyclical, but now, because of the lower gas prices, a lot of those cyclical plants are becoming more base-loaded. So things will change. One of the things we do know is the more up and down a turbine has, the worse for the turbine oil. So our turbine oils perform best when running hot and running long. So in our refineries, we actually don't have many varnish-related issues because we're running 8,300 hours a year, and it's hot and it's flowing, and they're kind of, when we kind of talk to them about varnish issues, they kind of wince and say, oh, we don't get it. We're not having those problems. And then we come to them and say, well, we've got even a better oil than you currently have. And they're saying, well, we're pretty happy with what we have. And so it's really just the operational aspect of things. Because they run steady state, base loaded, they're not seeing the issues that many others that are in the cyclical market would see. And then in that cyclical market, we know, we talked earlier today, or yesterday, about, you know, like the renewable aspect of energy production. And that number's somewhere around 6 or 7%, and that's tied to solar and wind. But as on cloudy days or non-windy days, the gas turbines have to fire up. Or then as we hear from a lot of the utilities, that on day-to-day gas versus coal pricing, you're going to flip back and forth. So the ability and the beauty of the gas turbines are in a fairly short startup period, 6 to 8 hours kind of thing, versus a coal-fired power plant at a 24 hours. So anyway, that gives a lot more cycling. And so we have kind of definitions of what we would consider high cycling, and basically anything that starts and stops more than once a week. So about 50 cycles a year is a high cycling plant. And then you can certainly have, sometimes it's 2 to 3 times a week that the plant is up and down. Each time that turbine cycles can be detrimental to the oil, and then detrimental to the oil meaning it could result in a no start or a unit trip. Also, we've seen elevated firing temperatures, and we had a slide yesterday that showed those firing temperatures going higher and higher, and as they go higher, we improve efficiency, but that temperature gets translated oftentimes to the bearings. When that firing temperature of the bearings increases, then my lube oil temperature increases. So it's just another stress on the oil, just that you don't typically see in steam turbines. And putting it in perspective, a steam turbine oil, we've got customer reports that, hey, I've had that turbine oil in there for 30 years without issue, and it's the same oil charge. And that's largely a steam turbine is running cooler temperatures, less strain, less up and down on it. So it's kind of in a much more forgiving arena than the gas turbine oils are. So our emphasis to help the industry has been on this varnish issue in these servo valves, and I'll explain in a coming slide. Why is it the servo valves? Why is it not a thrust, a thrust bearing or something to that extent? And so this tries to give that picture here. What we're looking at is this would be a gas turbine that has got a combined hydraulic and bearing reservoir. So this is namely the GE series that use the turbine oil also as the hydraulic oil, and Alstom has that same design where you're going to share that reservoir and ask that turbine oil not only to be a turbine oil and protect the bearings, but also be a hydraulic oil. So in some respects, it's asking a lot of my poor little turbine oil, but hey, we rise to the occasion, and it's a challenge. And so that gives us an opportunity to kind of work around the designs that are in the market. So that's one type of turbine you'll see out there. Then you see gas turbines, and maybe it's the Siemens Westinghouse 500 series or the Mitsubishi 500 series. And those will have separate reservoirs. And so the separate hydraulic reservoir allows you to have, maybe you've got a 300-gallon hydraulic reservoir that you're going to change that oil out every 3 years because it's fairly cost effective and it doesn't take a lot of effort to make that change. Whereas this, the gas turbine, you want that to run 7, 8 years, go overhaul to overhaul. So to make that change is a lot more problematic, expensive than to make a change in the turbine that has the separate reservoirs. And basically in these turbines that have the separate reservoirs, we do a lot of turbine inspections, and at overhaul time, we're getting our heads into those bearing cavities and seeing nice clean bearing surfaces, no issue. And then the hydraulics, like I mentioned, most customers are doing oil analysis and making those changes on maybe a 3-year kind of interval. And then again, no issues there either. And then lastly would be steam turbines. And steam turbines typically have separate hydraulic reservoirs. And typically the hydraulic reservoir is a phosphate ester or EHC fluid that is a fire-resistant fluid. So that's kind of a different animal that doesn't get itself into that varnish business like a turbine oil might. And so you can look and see with those 3 major categories, yeah, all 3 of them are maybe going to present a bathtub ring, and that's just a ring in the reservoir that shows some level of deposit. And basically it's in the reservoir, it's not impacting operation. So we kind of give it a light gray check here. All 3 are going to have, the bathtub ring, and then all 3 are going to have maybe some thrust-bearing varnish deposits, but it's going to be minimal. And I've done a lot of turbine inspections. I see a little bit, but it's not causing the unit to trip or not start. It's something that's dealt with at overhaul. So when you hit your 48,000 hours, you're changing out your thrust bearing, and that's kind of the end of that conversation. Same kind of thing we see in the main journal bearings. Yeah, at overhaul, I'll see some mild varnish. It's not impacting heat transfer. It's not causing the unit to trip. So it's it's kind of a non-event for most people. You can see some fouling on an oil cooler. Then when you see fouling on an oil cooler, unless your water or temperature capacity limited, it's typically not an issue, and maybe it has you back off a couple megawatts because of your restriction on temperature. But it's not causing that cooler to trip offline because of fouling on the cooler. But here's where the problem is. It's the big red check, and the big red check is in the hydraulic servo valves. These hydraulic servo valves are 3-micron clearances. So it's a tiny little valve that I need to have 3-micron clearances versus see my clearances in a thrust bearing might be 300 micron. In a journal bearing, it might be 180 micron, kind of the size of a truck compared to this 3-micron clearance. And it's that 3-micron clearance that causes these servo valves to trip offline. And then for those of you not familiar with the term micron, to give you some perspective, a human hair is about 70 microns in diameter, and a human eye can see about 40 microns. So we're well below what a human eye can see. And so if you visually look at an oil and say, well, that looks clean, that's not good enough to tell you, am I building deposits in my oil? So anyway, all this kind of speaks to where the issue is, and that's the most important thing about solving a problem is knowing what the problem is. So we know where the issue is, and now let's work to develop an oil that can solve that. This is some pictorial representation of where that issue is, and those of you that operate this type of equipment, you've seen this stuff torn down before, but the big thing is here, when we talked about the air-fuel ratio, and here's my air side, that's my jack shaft linkage that goes up here that controls my air into the turbine. And what this jack shaft does is goes up, and it only moves about 1.5 inches or so, but it's enough to turn this ring gear, and that ring gear turns the damper. So if I don't get the right movement, I'm not going to get the right air-fuel ratio. And that's where my servo valve lives down there that's fed by the hydraulic system. This is my gas valve here. And so this is where we're going to control the gas side of things. And again, if I'm offset by a little bit in here, that's enough to trip my unit offline. And then here's just what that spool valve looks like. And this one is nicely varnished up by us. And here's a clean one. And that varnish, that level of varnish that looks minute, I mean, visually you can see, but that varnish is sticky. And that stickiness gets in that servo valve and doesn't allow the valve to fully travel. So then my air-fuel ratio is off and the unit shuts down and you've got demand penalties you're paying and people are upset. Because of these issues, their customer base has been very innovative on a number of different workarounds. And okay, we've got the oil in the turbine and I'm having these problems. What can I do to improve my operation? So these are what they call mitigating strategies. And it is pretty neat stuff that unfortunately the customer has to devise largely on their own, largely going to user groups, largely hearsay, I heard this worked for them and that type of thing. So I'll just kind of give you a quick flash down some of the things that are going on. One is kind of the advent of some new oil analysis technology. These technologies were around for years, but didn't really have much traction. People weren't using them too much because there wasn't a whole lot of benefit to them. Now, because of this varnish issue and a lot more study work, had there not been a varnish issue, we wouldn't be talking about Ruler or MPC. Because there is, all of a sudden, it's become a pretty nice tool to help you, the customer, understand, hey, am I going to have a problem here in the near future? So the reason I bring this up is the world of oil analysis has improved itself over the past 15 years, and including, you know, some of the work we do with Ruler, and Ruler just looks at the antioxidant reserve. MPC is membrane patch colorimetry, looks at the color of the deposits in the oil, and ultracentrifuge spins the oil at a high RPM and then looks at deposit formation. So there are kind of some unique tests that are in the market to help you, the customer, understand, hey, am I going to have a problem next year, kind of thing. Then the whole world of filtration has blossomed into many different technologies and ideas, and most of them are pretty good. Some of them don't do much, but and you spend a lot of money, you don't get a whole lot of benefit for. And we have our personal opinions on some of the technology because, and again, our plant sites are using this equipment and oils and that kind of thing. And then we work heavily with the customer base to hear, hey, were you happy with this or not with that? So we've got our own opinions, and we've seen some pretty good things. But there's a laundry list of different types of filtration technologies that are out there. There's also some tricks of hydraulic circuit heating, where people will take heat tape and heat that hydraulic circuit. Remember I said when the turbine shuts down, the oil gets cold. When the oil gets cold, these soft varnish deposits come out of solution. It's a saturation thing. So when they come out of solution, they play it out in the dangerous areas. We don't want them to play it out in our servo valves and in our filters and that kind of thing. So some of our customer base, even our own plant sites, have gone with the idea of electrical heat tape on the hydraulic sector to keep everything warm. And then there's another, you also want to keep it flowing, and that's where some people are using the servo valve bypass plates. That allows constant flow. Otherwise, when the unit shuts down per design, that hydraulic leg is stagnant. There's no movement, and then it's exposed to ambient temperatures. So no movement, and then 50-degree temperature is kind of a recipe for the deposits to come out of solution and cause a problem when you go to start it on a Monday morning. There's other things that are being done, like main full flow filters in parallel. And so this is mostly, I call them the spark heads, guys that think, people that think that all of varnish is caused by electrostatic spark discharge. And there's a lot of people that have kind of jumped on that bandwagon and feel that spark is the start of all bad things that happen in a turbine oil. And we think it's a potential, but we don't see it as the #1 cause. Anyway, long story short is people will put their full flow filters in parallel to reduce the velocity through a filter, which there in turn would reduce spark. So just a strategy that's out there. Some people even remove the hydraulic filters. They feel like there's a lot of spark in that hydraulic filter. We don't recommend that, but it's just something that's being done. Offline servo valve manipulation, that's just stroking that servo valve, the servo valve bypass plates, or some customers are in the business of frequent servo valve changes. So they might change it every 6 months, and it's $3,000 a servo valve. So those kind of costs can add up. A GE Frame 7 FA can have 7 servo valves on it. So some people have moved in that direction, that they just go with a high frequency of servo valve changes. We feel that none of these are really needed. What we need is just a better oil. And that's what got us back to our rig testing. So what we did back in our Paulsboro facility is we got to get a better understanding of, hey, what's going on in the real world? What does a turbine look like? Where are the issues happening? So this is just a representation of actually one of our own plants' DCS screens, where we're showing, this is on a Frame 7 FA, and we're ramping up. So our red line is the valve command for the fuel valve, our green line is the valve position, and then the blue line is the power. And what we're looking at is anytime there's a offset, that's a potential for that unit to trip offline. I've got customers that say, hey, I can tell, there's a lot of great oil analysis stuff going on out there. I get customers, I can tell when I'm starting to have a varnish issue when I look at my screen and I can see that there's an offset larger than I would expect. That tells them that they're starting to get like stick-slip friction. So anyway, this helped us to understand, hey, when we build our rig test, we knew we wanted to have a valve in there because that duplicates what you're seeing, but we wanted to also get a sense of how much offset would we accept. And so this helped us in that conversation. Also, you know, we call open your equipment and look kind of philosophy is we've got a lot of good oil analysis data out there, a lot of things you can see, but the most important thing is to look at the equipment. And so this is our last chance filters, and here's a nice clean one, and here's one that's fouled. And so it's readily apparent, and so our lube engineers, sales engineers work with customer base when the unit's down to pull a last chance filter and do a visual inspection and compare it to the oil analysis that they're seeing to help understand, hey, where do you think you are in the lifespan of this oil? So it's good to get your eyes on the equipment, and then also, if you can, pull the servo valve. And if you pull the servo valve, take a look at that spool piece, take a look at that pencil filter. And then that gives you a clear indication of, hey, am I expecting trouble here in my near future or not? So we use the combination of what we're seeing on the screens and then visual inspections. And that helped us build our rig. And this is kind of a representation of what our rig looks like. Basically, we've got, we can start with the pump. From our pump, we've got a splitter that goes to a climate-controlled chamber where our servo valve is. Again, these rigs are designed to accelerate what you would see in the field. So we don't want to build a rig that lasts 50,000 hours. We want to have it, you know, fairly rapid decomposition of the oil to show us how one oil would compare to another. So what we do is with this climate-controlled chamber, that's where we put our servo valve in. And then we, the oil would flow around that. We'd go through a heat exchanger, through a filter, and back to the reservoir, and like that. And this rig, we've got 6 of them in our Paulsboro facility, probably about the size of this table with the components and that type of thing, and then the climate-controlled chamber. And so what we do is we run this cyclical like a lot of the power plants are run, and so we run it 5 days on, and then on Friday night when the guy, before he goes home, he shuts it down. And so when he shuts it down, he looks to see that valve stroking to see if there's an issue on valve stroking. And then Monday morning, he fires it back up, and he looks to see if there's a valve stroke issue on the restart. And that's when we look for, you know, that differential that we don't want to see in an oil, and that's what we develop an oil to last as long as we possibly can without generating stick-slip friction in that servo valve. And I am quickly, I got about 5 minutes left, so I'll chew through this real quick. This is just our servo valve and a representation of stick-slip friction. Basically here, this is what we want to see. The valve coming right to set point and staying, not hunting, not seeking that set point by stick-slip friction. And this is an example of overshoot, then undershoot because of stick-slip friction. This is, again, we're not relying 100% on this valve stick. We're also doing visual examination of the equipment here, and then we're also doing oil analysis that might condemn an oil. So we're looking at it in 3 different ways. We're looking at the valve stick, we're looking at oil analysis, and then we're looking at the components. So here's the oil that we've worked up, and we call it a balanced formulation. When we bring an oil to market, we need it to do wonderful things in a lot of different categories, not just excel in one aspect. So real quickly, this is like our deposit control, air separability, oxidation stability, filtration, foam, anti-wear, and rust. So you can't just develop an oil for one attribute. You have to take a look at the big picture, and then we use the spider charts to help us, you know, keep that focus. here's again just the stick versus no stick at a certain time frame. Here's kind of the results of our valve stick testing. And so what we have here is a number of different oils that are in the market today and then run in our rig testing. And these are hours till valve stick. And then what we've done is many duplicate runs to confirm that this data is meaningful. And as you can see, with the new oil that we brought to the market has done a lot better than current oils in the market, and then even better than what we thought was the best oil in the market at one point in time. So it was a pretty good learning tool for us to see what does today's turbine oil market look like relative to varnish. And here's the proof is always in the pudding, these servo valves. So what we do is annual inspection on these servo valves to confirm that, hey, our oil analysis is telling this, and we got to document that by visual inspection. So just real quick on system prep. Again, when I started, I talked about we could have the greatest turbine oil in the world, but if you didn't clean that system prior to it, oftentimes you're going to have failure. And oftentimes I use the term a half-life. If you were getting 7 years on your old oil and you just did a drain and refill, you might only see 3.5 years on that next charge because you left the residual behind. So there's a lot of good guidance documents on how to properly flush that turbine. So, with a minute to spare, my summary is that, we recognize there's an industry issue. We recognize gas turbines' place in power is going to continue to expand and expand, and we just want to be part of that solution. So, if you will, I'll take questions.
Any questions?
Hi, Joseph McCartney, Johnson Matthey. Do you have any concerns about the possibility of the lubricant having an effect on the catalytic aftertreatment, the SCR, or maybe even more importantly, the CO oxidation catalyst?
No, because there's no interface there. This is not going through the exhaust. It's staying uniquely confined to the lubricant system. It does have a demister that pulls it and takes it out of stack, but so it wouldn't come across a catalytic converter.
Okay, thank you.
Max Sherman with SIGA. You focused, your test rig on GE equipment. Are you seeing the same issue with other manufacturers, combustion turbines?
I would, not to throw anybody under the bus, but it's GE and Alstom have the combined hydraulic reservoirs, so that's kind of where the problem or opportunity exists.
Any more questions?
And just one more teaser part of this too is we're working with some of the OEMs on higher efficiency oils. So that's some pretty neat stuff that is kind of coming down the road for us.
Okay, that's it.
All right, thank you.
And that brings us to our first break. We have a 45-minute break. If everyone wants to get a cup of coffee or walk through the showroom, be back here at 11 o'clock for the third and fourth presentation of the day. Thank you.